I feel like, after however many episodes we've had, we would have the sound check sorted, we'd have the internet sorted. But alas, always something new.
I like to think that the
That's good.
radio and or podcast professionals out there also have these problems, which makes me feel good because it means we're doing it right.
I think you're right. I think we're just more straightforward about it. Like we just, or maybe more lazy,
Right.
in that we don't edit this stuff out. We just use it for our wonderful cold opens.
Exactly. All those people out there like throwing just piles of good money at post production nonsense. Fools.
There's a post to this production. Well, welcome, folks, to another wonderful and well thought out episode of Science Actually Presents the Nerd and the Scientist. Benjamin is waving at you, but you can't see that because this is an audio medium. But just know that he was waving at you really enthusiastically.
Very enthusiastically. Thank you all for tuning in. And a huge shout out to our first listener in Africa. Thank you, Uganda. We love you. And thanks to you, we now have a listener on every continent except the cold one. We're looking at you, McMurdo Station and Amundsen Scott Station and Palmer Station. Why don't you guys download our thing now so we can have, total global domination over the SciComm podcasting thing? Please.
I mean, I feel like, Africa, there's just one download. Every other continent, with the exception of Antarctica, there are multiple downloads, which is really encouraging. and thank you all for listening, or at least downloading, having a listen for 30 seconds and deciding not to listen. But Antarctica, I feel like there's got to be so few people living there that we could just email all of them by hand, not even like a fancy computerized way. Just like,
Yeah.
dear McMurdo Station,
What's up,
please
guys?
download our podcast.
I bet you they wouldn't mind getting some swag brought in on one of those planes that land on skis once a month.
Ski planes?
Yeah, have you seen those planes? Huge cargo planes that land in Antarctica, and where the wheels come out, they actually come out with skis in some situations.
No.
Yes, in some situations. In some situations, it's
the
wheels, but some situations, actually, yes, skis.
Picturing the wheels coming out as like giant ice skates on the bottom of the plane. And the plane like rocks up to the Antarctic station and just does one of those like to the side skid landings and snow flies everywhere. Anyway, enough about that.
Enough about that.
What are we talking about today, Benjamin?
Well, let's get things going. Let's get things on track here. A couple days ago,
got the juices flowing.
Actually, this has been a problem that's been bothering both of us for a long while. And here's the most recent example of it. Aaron Reich is a reporter for the Jerusalem Post, and he reports on a lot of their science articles. And when he tries to describe objects floating around in space or coming near Earth, whatever, he tries to do so in a relatable context, because when you tell the average person that there is an asteroid passing by, 100,000 miles away, or it's, it weighs however many tons, it's not exactly very easy to visualize. And just this week, he released that an asteroid the size of 8 Taylor Swifts passed by on Tuesday, 2 days ago. And he does this often with other wonderful units of measurement, such as Canadian geese, ducks, capybaras, bulldogs, beavers, chickens, Barbie dolls, hot dogs, Big Macs, Titanics, narwhals, alpacas. He even calculated the value of one asteroid to be equal to 40 million Elon Musks. Now, while we all appreciate the comic attempt to try to tell people the different sizes of things, not everybody understands how big Taylor Swift is. I assume not.
I just I missed that one. I know the work that Aaron's been doing, and it's all in good fun.
Mm-hmm. Mm-hmm.
But Taylor Swift as a unit, I don't know. Like he did when I had that brown dwarf that I found last
Yes.
year, and I wrote this cool paper about this ultra cool dwarf star that has a temperature that's really really low. It's like what was it? It was like the same temperature as a pizza oven,
Mm-hmm.
um, and I thought that was a cool comparison. And the temperature is about 1/10 of the surface temperature of the sun. The sun has a temperature of like 6,000 degrees, and Aaron goes, "Yep, your star has the same temperature as 5 cups of coffee."
Cups of coffee. As if breaking it
And
down
I
to a
just
pizza oven wasn't enough. It needed to be broken down further.
no. Oh god, but no, it's tough. It's tough to actually find relatable units to use when we're discussing things in space that are otherwise so far removed from our life, right?
Right.
So like um, people talk about the distance to the sun as an astronomical unit,
Correct.
right? 1 AU. I'm assuming you've heard of AU, and AU is not just the suffix on Australian websites .com.au.
I
Fun
thought
fact.
it's something you Australians yell at each other. Hey, you, get over here.
That too. Um, but like if you tell someone that the sun is like 150 million kilometers away or like 100 million miles away, that's not relatable, right? Like
Right.
you can't hear that and go, oh, sure, I know how long it would take me to walk that. It's just like a massive number, and you're like,
Right.
oh, that's super far. And then you realize, okay, so light, the fastest moving thing that we know of in the universe, takes 8.5 minutes to travel that distance. That's a light minute, or 8 light minutes in this case. I feel like that's more relatable.
That's right. And the further away you go, the greater the distances, and then the bigger units of measurement you need to describe those distances. Like astronomical units are great, I think, within the confines of our solar system, and it helps understand everything, how everything relates to each other. Earth, as we discussed, is 1 AU away, but from the sun, but Mars is 1.5 that distance, 1.52
Hmm.
AUs away from the sun. So now it's easy to see it's just 50% further away from the sun than we are. That kind of helps put things in context. But then you start thinking about the outer planets. They're up in like Jupiter's 5 units away, and Saturn's almost 10, and then Uranus is double that, and Neptune's even bigger. And I found out that the Voyager 1 spacecraft is 163 astronomical units away as of
Wow.
January this year. It's insanely far.
Wow.
Insanely far. And if you multiply how it takes 8.5 minutes for light to get from the sun to the earth, multiply that by
Mm-hmm.
163. That's how long it takes a one-way trip message to get to Voyager. And then it has to do it again back. So
That's
it's
wild.
far. It's very far.
I think this also kind of goes back to what we've spoken about in previous episodes about how hard it is to remotely control satellites
Yeah.
and landers on planets, right?
Mm-hmm.
Because, like you were saying with Mars, even Mars, it takes about 12 minutes just to get the signal there one way. So you're talking about like 24, 25 minutes to get a return trip. If you tell the robot or rover, right, to do something, and the rover says, "Okay, I'll do it," signal received. That whole thing takes nearly half an hour.
Right.
So yeah, that's pretty wild. It's also interesting to think about how um, good the measurements need to be of the distance when we're measuring different things in space. So, like, especially for fast moving things in orbit, things need to be really precise
Mm-hmm.
in order to get their orbits right on. But we can talk more about satellites later on in the episode.
Sure.
but it's just like we've gotten pretty good at this stuff. We're figuring it out slowly.
I have a little fun one. What is a light year? Is a light year. It's the distance the light travels in a year. We just spoke about
Hmm.
astronomical units, and that's 63,000 astronomical units. So in a year, light travels from the Earth to the sun that distance 63,000 times. That's incredibly far.
Okay.
It's incredibly far.
Huh.
Um, but what's a parsec? What's the use of a parsec? It's 3.26 light years. How often do we need to use a parsec? And I'm
It's
gonna Han Solo this in a second.
okay. So parsecs, yeah, for the average person, a parsec isn't super useful. For us astronomers, parsecs are a more natural unit to use because it's not just that they're slightly bigger than a light year. They actually tell you something about, or you can figure out the distance in parsecs based on the change in a star's position over time. So like the moon and the sun, we see them rise and fall over a day, over a night, through the sky. Um, the rest of the things that are in the sky generally move a lot slower. So more distant objects, even the whole sky. If you've seen those great time lapses of the Milky Way rising and falling overnight, um, that kind of that whole thing shifts together. All of these more distant objects, they seem to move together from night to night. But what's really cool is if you take a measurement of one of these stars at two different times in the year. Let's say like you separate it by 6 months and you make a measurement in January and you make a measurement in June. Um, our position relative to the star will change as well because we're on the other side of the sun. And so basically, when the angle that we see between the position that we measure at those two different times of years changes by an arc second, which is basically there are 60 arc seconds in a arc minute, and there are 60 arc minutes in a degree, right? Like you have 90 degrees
The
as a
angular
right
degree?
angle. Yeah, exactly, because you're looking noise. It's kind of like an angular distance, right? So in the same way that if you hold up a pencil at arm's length and you shut your eyes and you open one eye at a time, you'll see the pencil kind of shift positions. So that shift in positions of the star will be able to tell us how far away it is, how many parsecs away. So for every arc second that it shifts from side to side, it's 1 parsec distant from us.
Excellent.
So yeah, that might have been too deep into the
That
world
was
of
great.
angles and trigonometry, but
So,
oh god,
so
I know what's coming.
if the Kessel Run in Star Wars is 18 parsecs long, and Han Solo managed to do it in under 12 parsecs, that means he had to find a way to shorten the distance of that run. And he did so by skirting really close to the event horizon, but not falling into of black holes in something called the Maw cluster. Does that make sense? And if so, by the way,
I
getting
think,
incredibly
oh
close to a
god,
black hole like that, just to skirt a few parsecs off of a certain route, does that make him a time traveler?
I don't know if George Lucas had planned this, knowing that a parsec was a unit of distance and not
Or just
time,
sounded cool?
or just it just sounded cool and he just went with it anyway, or if it was something that was said in the moment, they just they went with it. But yeah, like for years, for decades, it was people just thought parsecs were a unit of time because it sounds like sex or seconds.
Right.
And that's wrong. Yeah, in a Han Solo movie that came out a couple of years ago, they did try to correct that by saying that like this place that they were going to in the Kessel Run was engulfed in this weird storm of electromagnetic radiation that would destroy any ship. You have to kind of navigate through that storm. And it was, there was like the Kessel run was like a set path through this storm, and nobody could find a faster route through it. But he found a faster route through it that was a shorter distance, therefore taking less time. So, yeah, we should do a whole episode on things that are not quite right in not even in sci-fi, just in just in Star Wars. Don't get me started on lightsabers. But yeah, that's for another episode.
I just got back from Disneyland. Try to go to Disneyland and not buy a lightsaber. We got one. We got one.
Nice. You walk around the house going.
No, my son does. But when he's not home, yeah, I do.
Nice. I think it's about time for our break.
All right.
Is there a particular ad that you or a particular product you wanted to tell us about?
I got one. Step right up, ladies and gentlemen, and feast your eyes on the culinary marvel of the century. Introducing Metagetti. Are you tired of the same old spaghetti, lacking that cosmic touch? Well, fret no more. Metagetti takes your traditional pasta experience to a whole new dimension. Literally. Picture this: spaghetti cooked to perfection just like mom used to make it. But we're taking it further. We're taking it beyond the ordinary and straight into the heart of a black hole's event horizon. That's right, folks. Your favorite pasta is getting spaghettified in the most extreme environment known to humankind. Imagine the flavors being stretched and twisted in the gravitational.
Looks like these satellites are going to hit one another. Then you say, "Oh no, it's fine. They're just really big icons that they use to do the visualization.
Right.
Surely they're not actually that close." But what I've found out is that satellites actually have to do an incredibly high number of autonomous collision avoidances, right? So SpaceX, which has, I think, on the order of 4,000, they have 4,000 different satellites. So they actually had to do, on average, 12 avoidance maneuvers each, right? So it's not like, only one of the satellites happens to have had a chance encounter with another one. All of them have had multiple encounters and have had to use this automated system, to avoid crashing into them and creating this Kessler Syndrome, which I didn't explain, but basically is the idea that if an explosion of a satellite happens in space,
Right.
That explosion will create tens of thousands of pieces of debris.
That's right.
And those pieces of debris will have a chain reaction and hit other satellites and other things that will create more debris until we get to the point that basically the entire planet is surrounded by clouds of
Bullets.
debris. And that would be, they're basically bullets in space, right? Like even a fleck of paint moving at those speeds.
Right.
Right? Because you're talking about things that,
Speaking of the SpaceX satellites, of which they're sent up in groups called constellations. One ship shows up and it sends out just fires them off like a railgun, just a stream of satellites, which eventually spread out over time, and they create a constellation around the Earth. Many rings of SpaceX communication satellites that are now currently have like a little patchwork net around the world. But those have self-correcting systems, but those will only last a certain long time as long as they have fuel to do so. Otherwise, they're just gonna, I don't know how they're gonna take care of it. China has a history of launching stuff into space without much concern as to where the initial stages or boosters go. They try to aim it into the ocean, but if they don't, they don't. And there is one case of a Long March 4 booster rocket that launched in the year 2000. And it's been tracked because it's a booster stage and it's just been tumbling around Earth for over 20 years. It's currently in about 300 trackable pieces. And there are other pieces, I'm certain, that we just can't track it because they're just too small. But
It's just too small. Yeah.
there are about 300 pieces of this booster rocket. This is just one instance of one rocket, one part of one rocket. That's in 300 pieces just going around and around the Earth. And it was also, according to what I read about the Kessler Syndrome thing, it was predicted in the 90s, I believe, and I'm sure we've hit it by now, that by the year 2000, the number of man made bits of debris in orbit around the Earth will surpass the number of more natural meteoroid objects that we knew about around the Earth.
Oh, interesting.
So there's more of our stuff up there than space stuff.
So I think on the Leo Labs website, they have about 20,000 objects that they display. I'm not sure how recently updated that is, but I'm assuming that it's pretty recent. And it's just, yeah, I think we're only expecting to get more. I think Starlink is planning to have a total of like 40,000 Starlink satellites over the coming decade. I mean, I know Amazon's doing a similar constellation thing, so I could definitely believe that. I'm not sure what the exact number of near Earth objects, naturally occurring near Earth objects are. But yeah, wow, I hadn't thought about that.
Yeah, that's cray
Whew,
cray. Uh,
it is.
I found out that to give a little context, a 1 kilogram piece of debris traveling at 10 kilometers per second, which is very easy to achieve up there, it has the potential energy to just destroy a spacecraft up to 1,000 kilograms in mass. So
Wow.
that's about a tenth, maybe a little bit bigger than a tenth, the size of the Hubble spacecraft. And this Hubble's pretty big. So an average communication satellite, if it hit something like this, it would just be bye-bye. And all this stuff is spinning around up in our atmosphere, or above our atmosphere. So it's pretty soon it's going to look like that movie Wall-E.
Wally, yeah. What is good? Maybe on a more on a more positive and
Depressing.
optimistic note. Uh, no, what is good is that one of the benefits of astronomy and the development of modern astronomy in terms of like big data and machine learning in astronomy has been that astronomers, when we see something flash in the sky, we want to figure out what it is. We want to figure out what kind of star just exploded, or a meteor passing near the Earth. And because of the way that satellites and satellite debris will reflect light from the sun, or in some cases reflect radio waves that are coming off the Earth at different frequencies, we can accidentally, as astronomers, identify these things and be like, oh wait, that's not a distant star. That's actually just a satellite or a piece of debris.
There's also a group called Clear Space, and their proposition for a mission called Clear Space One is a kind of weird, spidery looking satellite. It has its center bit and it has these long arms around it. And the idea is that these long arms, it'll direct itself towards a larger piece of debris, some useless thing that's
mhm,
just there. And the arms will grab it, and then it'll just pull it right. It'll basically grab it and commit suicide with it as it falls back down to the earth. So there are
mm.
some plans in place, some innovative, interesting future missions and spaceship designs that are going to try and help this growing problem.
And I think that there'll be a lot of interesting science that comes out of developing new approaches and new things that we didn't understand before to solve this. But I also think that in a lot of ways, this is an engineering problem. The same sort of people who are looking at how we can have more efficient spacefaring travel. I mean, if you figure out the fuel thing, you could basically have something like what you were describing, a giant spidery thing or an octopusy thing or like a net that that just goes through space and it speeds up to interact with a piece of debris and then slows it down. And basically, once it slows it down enough, it will just naturally, the debris will just naturally fall and burn up in the atmosphere, and then the thing can keep flying.
Yeah.
So it's, well, I think we'll get there. I'm optimistic about it because we have to.
Right. And some things could just be destroyed to a point where the bits, it's just, some things are, it is possible to destroy something up there, either with a laser or with a blast, to such a degree that the debris from that would be so particularly small, it no longer becomes an issue. Not vaporizing it, but something close to. And when you destroy something, it becomes non-issues. Potentially. I read one of those things. I thought it was interesting.
But even like a fleck of paint when it's traveling that fast,
yes.
I mean, you know, it just zooms past you and then, you know.
From where Kovi sits, he has a little panel of sound effects.
I'm sorry.
Nope, that was awesome. Oh.
This has been fun. I like talking about space.
I like talking about space.
I'm sure our listeners know.
I like talking about space. It's fun to talk about space. I try to talk about space at home, but it ends up being I don't have enough space in my closet for more shoes. Yeah. I guess I should be happy though. They did say the word space.
Nice. No, this is good, and I think that it's a bit of a public service to, you know, actually talk about how hard it is to think about these concepts in space without having some sort of helper, conceptual helper to you know, make things relevant and to understand these distances and the scales and the times. Not that parsecs are times, parsecs are distances. And like the number of satellites. But yeah, this has been fun. I like this one.
This is a good one.
Thumbs up. Yeah. I approve.
Well, don't say you like this one. That implies that there are previous episodes you just walked away just furious.
Hey, how do the listeners know? Maybe there are some secret episodes that we never published.
That's right. There was that one. It got a little weird. All right.
Okay, folks. Benjamin, where can people find you if they want to?
Thanks for listening, everybody. You can find me under the name of Science Actually. Find us on Facebook, and all of them, all of them: Instagram, Threads, Twitter, Mastodon, Hive, LinkedIn, the TikToky. If you want to, if you want to tick my talks, go talk them out, man. They're there, and daily science facts, lots of articles and things. Enjoy. Kavi, where can the people find you?
You, me, the people. I can be found at Fun Fact Science on all of the good procrastination and time-wasty apps that Benjamin mentioned, as well as Blue Sky, LinkedIn. Yeah, I'm everywhere.
Everywhere.
I'm like dark matter or neutrinos. I'm around. But you can find us both.
Foreshadowing.
You can find us both. Yeah. Oh. We should do an episode on dark matter.
What do you think? I think we should do that.
That would be fun. We should get somebody who actually knows what they're talking about, because dark matter doesn't matter to me.
Nope.
In my research.
I can't wait.
This has been another episode of Science Actually Presents The Nerd and the Scientist.